And welcome back, citizens, to Very Basic Refrigeration, Part 5, Expansion Devices. And here we have a list of expansion devices available. We have the capillary tube, the automatic expansion valve, the high side float, and the low side float. There's also a fixed orifice, but I'm not going to cover that. Now, why do we need an expansion device? Well, it provides a pressure drop or differential between the high side and the low side of the system, and it regulates the amount of refrigerant that enters the evaporator. Here's our first example, the capillary tube. This is used on mainly very small refrigeration systems, i.e. what you'd have in your fridge at home, and its small diameter of the tube and its length create the pressure drop. Now there are ways that you can calculate that, but we're not going to go into that here. Here we have the high side float, which is mainly used in larger industrial equipment. Now this provides a pressure drop as well as maintaining a level of refrigerant within the condenser that allows the refrigerant to flow once that level has been achieved. And on the other side of it, we've got the low side float, which provides the pressure drop as well as maintaining a level within the evaporator. This blocks refrigerant flow once the specific level is achieved. If the level goes down, it opens and allows more refrigerant in it. It just basically maintains a fixed level in the evaporator. And now we get on to the most common unit that's available, and that's the automatic expansion valve. Now this creates a pressure drop as well as regulating superheat. So let's have a look at the main parts of the valve. We have the sensing bulb, which is a gas-filled tube that senses the temperature. As the temperature increases, the pressure in the bulb goes up, and vice versa. As the temperature goes down, so does the pressure within the bulb. We then have the equalization connection, which is connected to the outlet of the evaporator, and it's so that the spring and evaporator pressure are the same as where the sensing bulb is measuring. Over the adjusting screw, where you can increase or decrease the superheat setting. And we have the all-important spring, which is there, that pushes up against the diaphragm and closes the valve. You can see a diagram of an expansion valve with its sensing element. It's on the outlet of the evaporator, and that's sensing the temperature there, but we also fit the equalization line so that not only is it sensing the temperature at that point, but also the pressure at that point. Okay, so let's jump into how expansion valves work. Okay then, there are three forces acting on a valve at any one time. Let's take a look at them. Firstly, you have the diaphragm. Now this is a thin metallic disc that is able to bend up and down and is attached to a spindle where it's also attached to the orifice, and as the orifice opens and closes, it regulates the flow of refrigerant through the orifice. There are, as I say, three forces acting on the bulb. They are the PB, which is the bulb pressure, which exerts a pressure downward. You've got the PS, which is the spring, which exerts a pressure upwards, and PE, which is the evaporator pressure, along with the spring pressure, exerts a pressure up against the pressure within the bulb. Here we have a valve that's in equilibrium where the bulb pressure, PB, is equal to the evaporator pressure and the spring pressure, so therefore there's no movement. And a diagram of the valve in equilibrium, which is hopefully got a superheat rating of around 6 degrees C. Now here we see an evaporator where the refrigerant level is much, much higher, and therefore the superheat is a lot lower. And in that case, the bulb starts getting colder and the pressure within the bulb goes down. So as the pressure in the bulb goes down, the pressure of the spring and the evaporator push up against the diaphragm and close the valve spindle, reducing the flow of refrigerant. Here we see the opposite effect where the refrigerant level is much lower and therefore the superheat is much higher. In that case, the bulb starts getting warmer, and that has the effect of the bulb starts sensing and getting warmer, so therefore the pressure within the bulb on the diaphragm is greater. It overcomes the pressure of the spring and the evaporator pressure and forces the spindle down, which opens the orifice and allows more refrigerant in. And the effect of allowing more refrigerant in hopefully brings the valve back to equilibrium again. Some valves have an additional feature known as MOP, which is maximum operating pressure. This is basically used to limit the gas density entering the compressor during a high load startup condition, thus reducing the running current of the compressor. If, for example, the pressure in the evaporator is low pressure, the gas molecules are sort of like balloons, they're quite widely spaced, but with a high pressure caused by high loading on the evaporator, for example, the pressure within the evaporator will be much higher and the gas molecules are more like cannonballs. And as you can imagine, it's a lot harder to pump cannonballs than it is to pump balloons. A quick but very important message to put across when you're changing a Danfoss expansion valve as shown here. When you're changing the power element, you'll start off with the element looking like that, and you'll have the orifice assembly, which is the spring, and at the other side on the left is the orifice. All importantly, you have an adjusting gear here, which gets turned and increases or decreases the spring pressure so you can modify the superheat. When you get a new power assembly, you'll get one of these tools. Most people think it's just there for adjusting, but it isn't. It's got a very important role to play, as I will show you now. It's important before you fit the new power assembly, you fit the tool as shown here. So you just pull on the hex and you slide the tool in, and that in itself allows you to fit the valve and it doesn't damage the gear, adjusting gear inside the orifice. Once the valve is fitted and everything's fully tight, you just pull that out and the hexagon will snip back in and you'll be able to adjust. This is a very, very common fault on a lot of expansion valves. There must be thousands of them out there that are marred. You can't adjust them because this hasn't been done when they've been fitted. Adjustment: if you turn the hex clockwise, it increases the superheat, so it increases the spring pressure. And if you turn it the opposite way, anti-clockwise, it will decrease the spring pressure, so therefore decreases the superheat. Apparently, it can take up to 20 minutes for the valve to get back under normal control after you've made a change. A quick look at some of the things that can happen within the evaporator. For insufficient superheat, you've got far more refrigerant liquid going in than you need. And the common superheat problems are decreased superheat, possible damage to compressor valves, and dilution of compressor oil. With increased superheat, you have a lack of cooling duty and an increase in discharge temperatures. Some of the main causes of insufficient superheat would be a lack of medium flow, air or water going through the evaporator. It can also be a big ice build-up, which will stop your heat transfer. An incorrectly adjusted valve or poor heat exchange, again, a dirty evaporator or ice build-up. Now, if we look at excessive superheat, we are using a much smaller part of the coil to do the cooling, the latent heat cooling. So therefore, we've got a large area of the coil that is not being utilised. So the main causes of excessive superheat are a shortage of refrigerant to the valve, could be loss of refrigerant, but not always. Block dryer or restriction in the liquid line, and excessive product load, or an incorrectly adjusted or faulty valve. A lot more systems nowadays are going down the way of using electronic expansion valves, or EEVs as we know them. There are three main types. There's a stepper motor, a pulse, and a thermal heating valve. An example of a stepper motor type valve. I'm not going to go into the ins and outs of how that works. There are plenty of videos on YouTube, etc., where you can find out how they work. Here you have a pulse valve, as it says, as the name implies. It pulses, and a piece of electronics reads the superheat at the end of the evaporator and opens and closes the valve to regulate the refrigerant entry. Here's an example of a thermal type valve, not used so much now, I don't think. The head is wax filled, it has a heating element in it and a temperature sensor in it, and the electronics pulse the heating element, and as the wax expands, it opens the valve and that regulates the refrigerant. Moving on to the EEVs now, we have a stepper motor controller, very clever bit of kit and very efficient, I believe. This shows the setup for an electronic expansion valve. You've got the EV in the normal place at the entry point to the evaporator. You've got a transducer on the output or the suction output and the temperature sensor, and they're all connected to the driver, and the driver reads the pressure and the temperature and sends out a pulse and opens and closes the expansion valve. Well, that concludes this lesson. Next time we'll put all these elements together and look at the system complete. Thank you for listening.